Hi, in this lecture, we're going to continue discussing the end-to-end machine learning process. So during the first part, we went over the first four steps. Remember, defining the problem. Then we talk about a little bit about the data collection and all the characteristics of good data. So now we're going to continue. First, we're going to wrap the how to handle missing data, the scaling, normalization or standardization, and also the labeling coding. So for that, we're going to use pipelines, and we're going to define that first. Then how to select and model, how to select the best model and how to train them, how to fine tune our models the idea is to find the optimal hyperparameters or the best hyperparameters for each algorithm. And finally, we're going to present the solution and launch it. All right. So why the end-to-end thinking is important? So the main purpose of defining this process from the beginning to the end is because it ensures reproducibility. The idea is that we want to offer some consistency throughout the whole process. So someone else, someone part of the team or a different, time, you can reproduce the same results. So that's why it is important to have random seeds in some cases and to define pipelines, which we're going to discuss shortly. Okay, the end-to-end thinking also provides a clear separation of the train, validation, and test sets to avoid overfitting, and at the same time, it offers a fair comparison across different models or algorithms that we want to test using the same workflow. Okay, so let's first talk about a little bit about the pipelines. So the idea of the pipelines is to chain sequential steps. So remember that when we collect our data, in some cases there is missing data, so we have the imputation process. Or this is not just imputation. Remember that you can delete, right, some variables or even some rows. Then for numerical variables, maybe you want to standardize or normalize the variables. And after that, you also would like to perform some future encoding for the categorical variables. So this is one more step. And then maybe at the end, you want to apply, a different model. So if it's regression, so you can do here some regression trees or random forest, to test different possibilities. So with the pipeline, we ensure that we have these sequential steps in order to get a standard process. So this is an example, impute missing values. That's like the first step of the pipeline, then to scale futures and fit at the end, fit a logistic regression. So we can create a pipeline where these three steps are clearly defined. So once you get the data, you just feed the pipeline and it will perform the three steps. So this works for the training, but it also works for the prediction. Okay, so in addition to the pipeline, in chapter 2 from our textbook, there is also they use the column transformers. So column transformers, sometimes there is a confusion between the two concepts, the pipeline and the column transformer. Well, the column transformer can be seen just as a single step of the pipeline. So the main idea of the column transformer is to apply it during the preprocessing, because remember that in your original data, in our data set, we might have different data types. For example, here we have numeric, we also have categorical, and there will be other type of variables, imagine text, right? Different things. So the transformation is different for numeric. So maybe for numeric, we want to do some scaling, normalization, or standardization, right? So this is our data. Once our numerical variables, once we have transformed them, then also for the categorical variables, we can apply some encoding, label encoding, one-hot encoding, right? So the process is different for the numeric and the categorical variables. It's not the same. And annual variables, we will keep them as they are. So these are they will pass through, they will keep the same format, the same structure. So the column transformer ensures that each subset of columns are transformed in the right way, the numeric the categorical, and also those variables that we won't want to affect. So at the end, once we apply the column transformer, we get our transform data. So again, this is just a single step in the pipeline. So they are not they are not like a similar thing. No, it's just the column transformer can be used inside the pipeline. Okay, just to be a little bit more clear, this is a representation. So pipeline, we have sequential steps. Step one, like here we can do the imputation for some values, also the standardization, right? And if you want to train a model. And the column transformer is just a single step, right, in that process. Typically in the pre-processing, we want to apply some steps only to one portion of the data, to some columns, and a different process to other columns. Remember, numeric variables or categorical variables, that's an example, right? And at the end, we want to concatenate our data set, our data, so we can keep, like moving forward in the pipeline. All right. So once our pipeline is clear for the preprocessing, how to transfer our data, and for the training, let's talk a little bit more about how to do the training in the best possible way. So for that purpose, let's talk about a little bit more about the strategies such as cross-validation. This is like the most basic way in which we can evaluate a model. So the idea is that once you have the 100% of your data, you need to split your data in training data. So this is just a suggestion. This is not mandatory, but it's suggesting 60% of your data. A validation data. This is a subset, 20% in this case. And finally, the test data. So the training data is the one that you're going to use to train your model, right? To estimate parameters for the model. In the validation data is where you're gonna check the performance of the model. And imagine that you want to test 3 different models, like model 1. This can be a linear regression. Model 2, a tree, regression tree. Model 3 can be a support vector machine or can be a random forest. So you train each model with the training data, the same data set, right? So you get 3 models. And then you can validate each model in the validation data, right? You get the performance and you can pick which one is the best. Among the 3 algorithms, which one has the highest performance. And once you have picked one of these 3 models, like which one is the best, then you can evaluate the performance of the model using test data, using new data. So please notice that the test data was used only at the end. It's not possible to use it, during the training or during the validation, because the idea is to generalize. You want to see how your model works. You want to see how your model works with new data, with unseen data. So this is the simple strategy. Now, something a little bit more elaborated and recommended is the K-fold cross-validation, which I already provided a video for this. So in this case, the K-fold cross-validation, it follows the same idea. So you have your data, 100% of your data, right? And then you split your data in 2. So one part for training and one part for testing. Typically, this is like 80-20. This is 80-20, 90-10, or 70-30. There is not like a fixed rule. There are some recommended values, again, 70-30, 80-20, or 90-10%. And then once you have split your data in training and test, so we do the following. So for the training test, we keep, again, the test data. Remember that test data, you will use it only at the end, once you have picked a model. So now, for the training data, the K-fold cross-validation, so it defines K-folds. In this case, K is equal to 5. So it splits the training set in 5 equal parts, right? So, and then there are 5 iterations. So there is 1 iteration per each fold. So if you have 10 folds, then you will have 10 iterations. So in the first one, this is the validation fold, not test, I will call it validation. In some cases you will find as test, but maybe that will be confusing with the original test set, right? So this is more like a validation fold. and call it validation fault. All right, so what you do is you combine these four sets like in a single table, you train a model and you evaluate the model in this validation set. So you get the performance. It doesn't matter if this is regression or classification, the idea is the same. That's for the first iteration. Now for the second iteration, this is your validation set, this one here. So with the remaining four sets or faults, with the remaining four faults, you train a new model and you are going to evaluate in this validation set. Same idea in the third iteration, in the fourth, and in the fifth iteration. So you get like you can get an average performance from here, right? So this is the process. You transform the data with the pipeline if you want. You can train the model and you evaluate the model in the validation set, right? And at the end, you will get like a mean value, because you have one score for this one score for this one for this one. In this case, we have 5 metrics or K metrics in general, right? And you can find the average of those individual scores. So you get the performance for a specific algorithm. So that's the K-forecast validation. You want to see the performance. And this is very useful if you want to compare different algorithms. That's a possibility. But also for the hyperparameter tuning that we're going to discuss later in this video, the cross-validation is always the way to go. All right. So for the training, it is important to be aware that our algorithms, in general, they have some hyperparameters. So there is a distinction between parameters and hyperparameters. So parameters are estimated when you're training your model. So they learn from the data. For example, for a linear regression, remember the structure of the linear regression, the way it looks. So it has a constant value, the intercept, right? And then it has some betas times each variable, right? Up to beta k times xk. So here in the linear regression model, our parameters are the betas, beta 1, beta 2, up to beta k. Those are our parameters. And these constants are estimated using data. They learn from the data when we're training the algorithm. So training here means to compute these values, right? Now, those are parameters. But on the other hand, we have hyperparameters. They don't learn from your data. You need to predefine those values before training your models. Actually, they are important because once you define them, they will kind of like affect the performance of the model. They will guide the training. So, for example, the decision trees. It doesn't matter if it's regression tree or classification tree. There are some hyperparameters, like the max depth. It means like the number of levels of the tree, like how deep is your tree. A minimum number of samples to make splits. So you can define different hyperparameters. And again, you don't know those values before checking the model performance. And they don't learn from the data. So you need to test different values, and there are some strategies for that. In the case of popular algorithms such as the K nearest neighbors, KNN, so a very important parameter is the number of neighbors, right? K, the number of neighbors, K. So that's the hyperparameter. And again, you don't know which value to pick initially. You need to check to test different values. So for that purpose, we have the hyperparameter tuning, which is to find like the best set of values for those hyperparameters. So there are two popular strategies. So the grid search and the randomized search. So the grid search is like you define an interval or some specific values for each hyperparameter. This is like you tried all the possible combinations, for each hyperparameter that you define in a grid. That's why it's called grid search. So of course, this is a time consuming, and also you need a lot of resources depending on the complexity of the problem that you're facing. But in general, grid search, if you provide like a large grid, with multiple possible values, then it will take time, right? Depending on the complexity. In the case of the randomized search, you need to provide maybe a like an interval, like a minimum maximum value or distribution, and it will explore the values randomly. Right? It's not going to explore every single value. It will do it randomly. It will take, like different values within the interval that the user is defining, right? Or following a specific distribution. So these two strategies will help you to perform the hyperparameter tuning. The way to check like how good are the like the parameter, the hyperparameters, is using cross validation. That's the only way. So every time the hyperparameter changes, so using cross validation, the splits, K4 cross validation using the splits, you check the average performance to pick, okay, which is the best, like if we're talking about decision tree, so which is the best max depth, minimum sample split, or minimum sample in the leaf, or for the KNN, you will find the value of K, the N neighbors. So at the end, this is how it's gonna look our end-to-end machine learning system. So we collect the data, we're gonna transform the data. Remember that here we have different processes, right? Missing values, encoding. We are also standardizing our numerical variables. In some cases, depending on the data, you need to do some what we call tokenization, right? If it's text, you need to tokenize the text. Then we train our models, but the training implies this comparison of different algorithms. You need to tune those algorithms. You need to tune the hyperparameters of those models before you compare them. It's like you need to find the best version of each algorithm before you compare them, right? So this step takes a lot of time too. We evaluate the models, and this is really important. Even once your model is working in real life, you need to keep evaluating the model. You need to control the performance, right? And this is really important. We need to register the model. This is like controlling the versions. So every time you test a model, sometimes you need to change the model because data is changing, because maybe you are testing different algorithms and you found a new algorithm that is better. So it's important to have, the version control. For each of the versions, you need the parameter, the data that was used for the training. This is, like to have consistency, and also as a way to ensure that you have like how you found everything. This is really important, because in some cases, if there is a mistake, you can roll back and go to a previous version. That's a possibility too, right? Okay, what we learned in this chapter 2, end-to-end machine learning, in the second part. So pipelines are really useful when we want to kind of define a flow of steps. In this case, for the preprocessing and even modeling, we can use our pipelines. Please go over the examples, the code examples, where you will see, how to code this using scikit-learn. Cross-validation, it's kind of like the standard, especially K4 cross-validation. It's really important when you want to generalize an algorithm, when you want to avoid, like the overfitting problem. So cross-validation is a good way to identify if you're having some issues, like maybe your model is too good only for the training, but not good with new data. So cross-validation is the way to check that. Hyperparameter tuning is really important to find the best version of each algorithm, because you cannot use just the default values of the hyperparameters. Especially in real life, you need to test and you need to identify which one is the best. There are no formulas here that will help you to say, okay, is this? You cannot find them, with a formula, the exact value. The only way here is with experimentation. You need to test, different values and check the performance. That's the only way, using, of course, cross-validation. All right. So I'll see you in the next lecture.